Okay, in this video I just want to show how we can use a method of undetermined coefficients to find a particular solution to a second order linear differential equation. And so we're looking at a second order differential equation because the highest derivative is 2. It's a non-homogeneous problem because the right hand side is not 0, and you've been given some conditions. These are specifying the value of y at 0 and at 3. Sometimes you might see initial values of the value at 0 and the derivative. But you just need to have two conditions because you know you have two integrations that are going to surmount as a result of having a second order differential equation. Now to get the full solution here, we first got to find the homogeneous solution. And so I'm just going to write down the homogeneous problem, and that's where the right hand side is equal to 0. And the reason why we want to solve this first is that since this is a linear problem, any solution to the homogeneous problem will also be a inside the full solution to this. And so we recognize that to solve this, we make the guess. It's a very educated guess, but we make the guess of e to the rx. We substitute that in, and we develop the characteristic equation of r squared minus 4 is equal to 0. And so therefore we find two solutions, e to the 2x or e to the minus 2x. And I'm going to just write down the solution in terms of sinh and cosh, just because it's a very compact way of writing things down. So let's write a cosh x plus b sinh x. And if you remember, cosh x is a combination of exponentials. It's defined as e to the x plus e to the minus x all over 2. And sinh of x is defined as e to the x minus e to the minus x all over 2. And so if I wrote it as a combination, you can think about as a sidebar here. If I wrote this as c e to the x plus d e to the minus x, which you might have been tempted to write it as instead of here, this really amounts to the same thing. There is an a times e to the x, and there's a b times e to the x. That would combine, that gives you c. So c would equal a plus b. Likewise, there's an e to the minus x in the cosh, and there's an e to the minus x in sinh. It'd be an a minus b would have to equal to d. So there's a relation to that, but all you care about is getting what these arbitrary conditions are. I'm going to write it this way just because it's easy to evaluate at 0. And it's just a preference as well. But after we find a homogeneous solution, you're going to find now your particular solution. Now this is a unique solution that when I plug into, or say, satisfies this differential equation and generates that right hand side, it really is a function where its second derivative minus 4 times itself equals x plus e to the x. And the method of undetermined coefficients is really just a monkey see, monkey do with some educated processes to that of choices. But because I see an x and because I see an e to the x, I'm going to guess that the particular solution is some form of alpha x plus, I'm going to put a constant here, and then plus, I'll do rho e to the x. Now, the reason why I'm putting that constant there is because I see this x in there, and I just want to have the situation where I've had enough constants. Now, you may even see that there could be a problem with this. When I put that second derivative, that's going to end up being 0 on here, and I just get minus 4 alpha x, and we're going to end up choosing that beta equal to 0. But this is often a good exercise that if you happen to see terms like x, you might want to guess all the polynomials up to that. Likewise, if you saw x e to the x, you might want to guess that all the polynomials as a coefficient to e to the x up to there. So just kind of as an addendum here, if there was another function here, you might guess something else in there. But anyways, this is my guess right here, and the goal is to make choices on alpha, beta, and rho such as satisfies that differential equation. So we're going to take two derivatives. So we're going to bypass the steps there because the first derivative of this is alpha, second derivative is 0. And of course, two derivatives of the exponential is just the exponential. And now we're going to plug that into our governing differential equation. And so we get rho e to the x minus 4 alpha x minus 4 beta minus 4 rho e to the x. And that has to equal to x plus e to the x. And if it's going to be a solution, this equation needs to be true for all x, or for all x in the specified domain. Now let's collect our terms that we have that are or like terms. So we have a rho minus 4 rho, so that's a minus 3 rho. We of course have a minus 4 alpha x. I'm going to put that as a plus and a minus 4 alpha x. And then of course we have a minus 4 beta. And that all has to equal to, I'll write it as x plus 0 plus e to the x. Now, in order to get this to equal for all x values, we're going to make selections on these coefficients so they match up with the coefficients that are over here. So what that means is that we're going to let 1 equal minus 4 alpha. We're going to let minus 3 rho equal that 1. And likewise, we're going to let minus 4 beta equal to 0. And clearly you can solve for each one of these. You could get a more complicated set of linear equations, but the goal is that we would just use some sort of elimination and substitution method to solve those equations. And if you get a contradiction, that means this is not a solution. And we have to go back to the drawing board and most likely make another educated guess. So we do see that alpha equals minus 1/4. So our particular solution, I'm going to write it back up here. Alpha has to be minus 1/4 times x. We do see that beta is equal to 0 to satisfy that equation. And we see that rho has to be minus 1/3. And that's our particular solution. So at this point, we're ready to go to our final step, which is generating our full solution. So our general solution, which we have not used these conditions whatsoever, is the sum of our homogeneous solution, a cosh of x plus b sinh of x, and then plus our particular solution, which is minus 1/4 x minus 1/3 e to the x. Now to specify these two conditions, a and b, these two constants, you can call them constants of integrations because that's exactly what they are. These a and b are satisfied by making sure that your function y is equal to 0 when x is 0, and when your function y is equal to 0 when x is equal to 3. So let's try to do that. I'm going to go to a different page to do that. And so let me just transcribe our full solution again. So we have y of x is a cosh plus b sinh of x minus 1/4 x minus 1/3 x. I'm just transcribing the solution that we have already discovered. So now we're going to evaluate at x equal to 0, and we want that to equal to 0. That's a condition that was given to us. It's an initial condition. So if you plug in x equal to 0 into cosh, that gives you 1. So you'd have a. Sinh of 0 is 0. And I have 1/4 times 0 minus 1/3 e to the 0, which is just minus 1/3. So that immediately tells you that a has to be chosen to equal 1/3. If you don't choose a to be 1/3, you will not satisfy that initial condition. Now our next condition is that y of 3, when x is equal to 3, y is equal to 0. So I'm going to be retroactive here, or proactive I should say, and put that 1/3 into that cosh because we've already discovered what that is. But we have 1/3 cosh evaluated at 3 plus b, which is the last unknown we got to discover, sinh of 3, minus 1/4 times 3, so minus 3/4, and then minus 1/3 e cubed. Now, of course, these are not scary. These are just numbers, and that's also a number. And we can just solve for b by adding these terms over to the left-hand side, subtracting that term over, and then dividing by sinh of 3. And so let's just write down exactly what we'd have for b. We'd have b 3/4 plus 1/3 e cubed minus 1/3 cosh of 3. And that entire expression would be divided by sinh of 3. And we really don't need to simplify this much further. I mean, if you want to get rid of the fractions, you can multiply top and bottom by 12. But it's not really necessary at this point. But let's just write down our full solution to this differential equation. We have y of x is 1/3 cosh of x plus that entire thing. I'm just going to put that in parentheses, times sinh of x minus 1/4 x minus 1/3 e to the x. And so now this solution satisfies both conditions, and it satisfies the differential equation that was initially given to us. And we can use this function now to evaluate your solution anywhere you'd like. Now, an often question is, how do I know if this is right? And there's really two particular ways that you can go about determining if it's right. One is, of course, just going through all the arithmetic and checking your work, which really probably the best way to do that is take two derivatives of y. Remember the differential equation that y has to satisfy is y double prime minus 4y equals x plus e to the x. So you could take two derivatives of this, subtract 4 times itself and show that that equals x plus e to the x, and make sure if you evaluate at 0 it's 0 and evaluate 3 at 0. And you could use a numerical differentiation tool such as Sage or Wolfram Alpha or what have you, or even Desmos, to verify that. Now, another particular way, speaking of Desmos, is you could look at a graphical solution. You could specify this function in your graphing calculator. And if your graphing calculator can take a derivative, which TI-89s and Inspires, as well as Desmos, can do very easily, and as well as Sage, I could graph y double prime minus 4y minus x minus e to the x. And if y is truly a solution, then if I were to graph this, well, it'd be graphing just the function y equal to 0. So that could be maybe a graphical solution or a graphical check to your solution. Hopefully that helps in terms of trying to find a full solution and also going through determining the unknown constants that you get after the integration.